Hello friends. So today we are going to solve three questions, and these three questions are from statics. So in the first question, it is given that a uniform disk of mass m, radius r, is supported by a massless string wrapped around a part of its rim. The surface of the disk is frictionless. Determine the tension in the string and the normal force per unit length that the string exerts on the disk. Suppose now the friction exists between the string and the disk. The coefficient is mu. Find the smallest possible tension in the string at its lowest point. In this case we have, so we can just draw the basic figure, and so we are given that we are having a disk. So this is a disk which is having a center and around which a string is wrapped, something like this, and it is fixed at the top. And we are given that r is the radius of this disk and m is the mass. Okay, so that is given to us. So in this case we are, first of all, let me redraw this disk again, and this is the center. So this is the vertical, and here we define an angle, and for this angle we can say with respect to vertical we define an angle. Let us suppose this angle is our phi. So it means this is one extreme of the string. Let us call this as our P1, and this is the other extreme P2. Okay. So we can just approximate that this P1 and P2, this is our P1 and this is our P2. So this angle phi is going to vary from plus pi by 2 from extreme one end to minus pi by 2 to other end. Okay, and at the vertical this value of phi is equal to 0. Okay, so this is the basic thing. Okay. And so when the angle is our phi at this particular instant, let us suppose the tension in the string is given as T of phi, because as phi is going to change, the tension in the string is also going to vary. Okay. And so here let us consider a small element, that is small element is of ds, and our center is of C. Okay. This is our center C, and so we are interested in a small element. So let me consider this is our center C, and we have considering a small element, and this small element is ds, and the angle of this small element is our d of phi. Okay. And r is the radius, therefore we can say that considering a small element d of s, and this length of this small element d of s will be equal to r times the angle, that is our small angle d of phi. Okay. And from here let us write the normal per unit length. So we can say our normal per unit length, and let us suppose that normal is given as our small n, and therefore we can say that normal on the element arc, we can say that our normal on the element, small element which we consider d of s, will be equal to n d of s, and d of s is r d of phi, so this comes as our n r d of phi. And here we have taken this small n as our normal per unit length, and if we consider that the total normal for our entire arc, so we can say that total normal and for the element, and let us suppose that is a capital N of phi, okay, then this capital N of phi will be equal to our n r d of phi. Okay, and but in the solution part we are interested in this normal per unit length because it is much more convenient to solve. Okay. And so in the first case there is no friction. Okay, we have two parts in the question, therefore in part A we can say we are given frictionless string. Okay. And in the absence of this frictionless, it is much more easier to solve. Okay. So we are, first of all, we are going to consider the vertical equilibrium. So we can say that our vertical equilibrium, and in case of this vertical equilibrium we can write that we have this is a center C and this is small arc. Right now I am just denoting this small arc with a single dot because normal will be much more easier to represent, and this is our normal, and we can divide this normal into two components. Okay. And with respect to vertical, the angle is taken as phi, so this angle will go also for phi. Okay. And we get this as our n cos of theta, and other will be for n sine of theta. And in the downward direction through the center we are going to have our mg. Okay. Therefore we can write that in vertical equilibrium the normal force on the arc vertical equilibrium, the normal force on the element, this is our ds element. Okay, I am represented it as a small dot, otherwise it has to be like a, this will be our entire ds. Okay. Small element ds will be equal to our r d of phi. Okay. And it's from here we can write its vertical component and the vertical component will be equal to our n r d of phi and our cos of theta, sorry, this is phi not theta, cos of phi. And like I said, we are going to cover this from minus pi by 2 to plus pi by 2. Okay, so we are simply going to integrate. Okay, and therefore we can write that integrate the upward component from this will be our phi and it belongs to minus pi by 2 to plus pi by 2. And this vertical component will be balanced by our mg, therefore we can write our total, this is our minus pi by 2 to plus pi by 2, and we have nr cos of phi d of phi will be equal to our mass times g. Okay. And if we evaluate our integral on the left side, we are going to get this as 2nr will be equal to mg, and from here we get our normal per unit arc length, normal per unit arc length, that is our small n is equal to our mg upon 2r. Okay, so we were able to find out normal per unit length. Now we come to our tension part. So we find out a tension in the string. Tension in the string. Okay. And the first case, part A, there is no friction and therefore there will be no tangential force between the string as well as the disc. Okay. So it means the tension will be same through the entire string. Therefore we can just write it as that this is our disc and we have a string wrapped around like this. So here will be tension T as well as here will be tension T, and in the downward direction we are going to have our mg. And for tension in string, so we can write this as our twice T will be equal to our mg, or we can say our T is equal to mg by 2. And so now we can, like I said here, this when the for angle of phi we have taken this tension as T of phi. It means our this tension is dependent upon our angle phi. Okay. Therefore, we can say that in case of our friction present, so we have our part B, and for that, so we have, this is our vertical, we have a center C, and at angle of phi we have taken that this is a tension of our T of phi. And suppose we consider a arc, and that suppose this is the arc and it is making an angle of d of phi small angle, and at this point the tension is dependent upon now T of phi plus small angle d of phi. And so let us call this as point as our A, and this is our point B. Therefore we can say that for element AB, and the tension at A, that is our T of phi, and at B is our T of phi plus d of phi. Therefore we can write that this our difference in the tension T of T, it can be written as our T of phi plus d of phi minus T of phi, and this difference in tension will be resulting in the, or we can say will be equal to the tangential friction force. Okay. So we can say this will be equal to tangential friction force. Okay, that's a different tension, and we can just represent, let me draw this approximately. So we have, this is our arc and this is point A and point B. So here we have our T of phi, and this is T of phi plus d of phi, and this tension will be approximately straight, not exactly straight in this direction, and otherwise it will be also in this direction. So net, the force of friction will be our equal to the difference between the two. And from here also we can say that if we can represent this entire arc as a small dot, so it is something like this. So we are having one tension in this side and other on this side. So therefore we can say the resultant will be coming something like this. Okay. So we can draw here also. So the resultant will be coming something like this approximately. And we also know the direction of the normal is same as this tension resultant. Okay. From this figure it is very much clear. Okay. And we will come to that later on again also. Okay. So first of all we can say that the tangential friction force, and we can write its our F element, that the friction force in the element will be equal to mu, and this is multiplied by the normal on the element. Normal on the element, which is our standard formula. We know that F is equal to mu times N. Okay, here the difference is we have taken as a element, so therefore normal on the element, and its equation we already know. Therefore we can write that our F element will be equal to mu n r d of phi, and like we said, this is nothing but our d of t is equal to tangential friction, and that is our F element. Therefore this will be equal to our d of t. We will use this particular equation later on also to find out. Okay, and now we come to the resultant part of the tension. So we can write one statement, and this statement is very important for in this particular concept. We can say that the resultant of two end tensions produces the normal on the element. Okay, so basically means, let me draw it once again here. So we are having two end elements, two end tensions. We are having T of phi, and we are having T of phi plus D of phi, and their direction is approximately like this. So their resultant will be somewhere here. So this is our T resultant. Okay, and the direction of the normal is same. Okay, so we can say the tension is nothing but our produces the normal on the element. So this is the one of the key concept in this particular question. Okay, and therefore we can write that our tension T will be equal to our N times R, or from here we can say our N is equal to T upon R. Okay, and furthermore, in terms of our normal element, we can write it as our normal on element, and that element is our N d of phi, which is nothing but our d of s, will be equal to T times d of phi. Okay, and therefore from here we can say that our N will be equal to, we can cancel out d of phi and d of phi, we get this as our, this tension T is, we can write for the sake of, will be our T of phi and divided by our R. And we already know one equation, which we, this equation. Okay, so let us call this equation number 1. So we are going to use this equation, and dt is equal to, so you can say, and let us call this equation as a 2. So you can say from equation 1 and 2, from equation 1 and 2, we can write that our d of t will be equal to mu, and we simply substitute value of this normal per unit length, per unit arc, and that is our T of phi upon R, and this is our R and D of phi. So here this R and R cancelled out, therefore we get our D of T will be equal to mu T of phi and D of phi. or we can just separate the variable. We can write this as d of t upon t is equal to mu d of phi. And this we are going to integrate, because like I said, this is our center C and we have taken phi, this point is phi is equal to 0, and the other extremes are phi is equal to plus pi by 2 and the other one is our minus pi by 2. So we are going to integrate this from our tension at 0 and tension at pi by 2. Therefore, we can say integrating tension at this will be equal to our t of 0, and this comes as tension at pi by 2, d of t upon d. Okay. And this comes as mu, and angle varies from 0 to pi by 2 d of phi. And this is quite simple integration. Okay. So we can write this as our, this will be coming a natural log of our t pi by 2, because its integration will be natural log of t, and if we substitute it, we will be getting this in, we can write rather it in fractional form. It will be either coming as t pi by 2 minus t naught, and natural log, so we are logarithm property, and we get this particular solution. Okay, and we can further resolve it, and we can write this in form of our exponential. So t of pi by 2 is equal to our t naught e raised power mu pi by 2. So this is our expression for our tension, and in case of the friction is present. Okay. And next, in the same question, it is asked about the our minimum value. Okay, so it means that we already calculated that our tension T in the first part is equal to mg by 2. Okay. Or in this particular case, we can just modify this, and we can write that at phi is equal to pi by 2. Phi is equal to pi by 2. So which basically means that if this is our disk and we are having a pi by 2 here, and at this particular instant here the tension is given as T, because here it will be slightly in contact with the disk or with the our disk. Okay. So therefore we can say at phi is equal to pi by 2, the tension and in specifically for this particular case phi is equal to pi by 2, we can call this a tension at the top will be equal to our mg by 2. Phi pi by 2 means for the other side also. Okay, so this will be our minus pi by 2, and here it also will be T. Okay. So the tension will be friction dependent, or we can say phi dependent in between this part only, between this one and P1 and P2. Beside this other part, this tension will be independent of our this angle, that is our phi, and therefore we can say that our tension at pi by 2 will be equal to our T naught e raised power mu pi by 2, and this is nothing but our mg by 2, because tension at phi is equal to pi by 2 is our mg by 2. So we can say that our tension minimum at 0 will be equal to mg by 2 e raised to power minus mu pi by 2. So this will be our minimum tension that was asked in the question. We come to the next question. And in this question it states that two uniform sticks are hinged on the ground and lean against each other as shown in the figure I'll draw later on. They meet at right angle with the right stick making an angle of theta with the horizontal. The left stick extends only infinitesimally amount beyond the point of contact with the right stick. The coefficient of friction between the two sticks is mu. Both sticks have the same mass per unit length. Determine the minimum value of theta for which the stick remain in equilibrium and do not fall. So we are given two sticks. Suppose this is our horizontal path and the left stick is making an angle of theta with the horizontal and the right stick is something like this and they are at an angle of 90 degree. And it is also mentioned that the left stick is a little bit longer. Okay, it is extends infinitesimally a little bit longer. Okay, so there's a portion left on the stick. And let us call this as A, this point as our P, and let us call this as our B. And they are having friction is there and they have the same mass per unit length. Okay. So let us say that our left stick is having a length of our LL. L stands for the smaller in the left, and the right one is having a length of our LR. Okay, later we can just solve it because it is not required. And from here, and we can also say that they are having, it is given that they are having same mass per unit length. Okay. Therefore, let us assume that the linear mass density of both the stick is our lambda. Therefore, we can calculate that our mass of our left stick will be equal to our lambda and its length, and mass of our right stick will be equal to lambda and our right length. Okay. And so from the figure, because this angle we have 90, this is basically right angle triangle, and therefore we can say that from triangle APB we can write that length of our left, length of our right will be equal to our tangent of theta. Okay. And with respect to mass also we can write this equation. So we can write this will be equal to our mass of our left, mass of our lambda, and the mass of right is equal to tangent of theta. Okay, so we can just write this equation both from the right angle triangle. Okay. And here we have to remember one thing, that this entire system is equilibrium. Okay, so let me draw this figure again, and then we can draw all the forces that are within this. So we have this at 90 degree. Okay, and so we can say that the normal will be acting in this direction, and we are going to have a force of friction that will be acting this direction. So these are the two forces that will be acting in this specifically. Okay. There will be other also, like a normal reaction at both the sticks, but we will do that later on if required. So for the left stick, we can say that there will be also a MgL G in the downward direction, and its length will be at a distance of our left divided by 2. One second. Sorry, my mistake. Angle is on the opposite side. This is not the angle. Angle is here. This is theta. Sorry, my mistake. So this will be 90 minus theta. So we get this as our theta, and this will be 90 minus theta. And therefore, this distance will be equal to our, we can write this will be equal to our L by 2 and cos of 90 minus theta. And this will be coming as our left, and we have this as sine of theta. Okay. And okay, so let us consider for left stick, for left stick, okay. And we find out the, you can say, the torque with respect to, this is A, with respect to point A. Okay, so at this point normal will be also there, but for A it doesn't matter. Okay, so we are not going to draw. And similarly for the other also, this is our point B and this is our P. So for left stick about point A, and therefore we can say that the moment about point A or left stick, because of this our this mg, we can write this as our tau of our, let me write this as tau of g will be equal to our mlg multiplied by the lever arm, that is our left distance and sine of theta. Similarly, we can find out with respect to point A the moment because of the normal n. There will be no moment because of the friction F, because it is along the same line. Okay. Therefore, we can say that tau of our n will be equal to our n, and the total length is our, this length of the lever arm is our total length of our stick, that is our AP. So multiply by our the lever arm. And for our, you can say, equilibrium, so you can say for equilibrium, we can write that torque because of G will be equal to torque because of the normal, and we can equate them. We get this as a mass of the left, length of the left divided by 2 sine of theta will be equal to 1 normal multiplied by length of the left, and this length and length cancels out. Therefore from here we can get that 1 normal is equal to mass of our left g and divided by 2, and we have this as sine, one second, this comes as our sine of theta. Okay, anything else? And similarly we can do for our other also PB. Okay, so it will be having in the downward direction, we are going to have our mass for the right of G, and this will be our length of R divided by 2, and we will having this cos of theta. Okay. And then there will be friction also, so this length is our length of our right. So same calculation we can do for our right stick also, that is our PB, and this we are going to take about this point B. Therefore we can say that for our PB about B, because if we take about B, the normal that is in this place will be, there will be no torque because of this normal and because of this normal also. Okay, so it is much more convenient, and therefore we can write that our torque because of our G right. Okay, and this is our, let me write, this is G left and G left. So this we get our it will be mg right, m right G by 2, and we get this as cos of theta. And similarly we get a torque because of the friction will be equal to force multiplied by our, here I missed one thing, length of right multiplied by length of right. And for equilibrium we can say that a torque equal, so we can write this as our mg right G length of right cos of theta divided by 2 is equal to friction because of our right, and their length cancels out, therefore we get friction is equal to mg mass of right G2 cos of theta. So we got two important things, friction as well as our normal equation. Okay, because we are interested in finding out the this minimum value of theta, and for that we are going to use the relationship between the friction as well as our normal. Okay. So we know that our friction force is less than equal to mu of n. This is a standard relationship in our statics. So therefore we substitute it, we get this our mgr G upon 2 cos of theta is less than equal to, we get this as our mlg by 2 sine of theta. We get this as mlg upon 2 sine of theta, and here this our 2 G and G cancels out. Okay, and we can write this can be simplified as our ml upon mr is, here term is missing, that is our mu. So this comes as mu times, and we, sorry, not mu times, but what 1 upon mu, and this comes as our cot of theta. And we know that our the ratio of the mass is nothing but our tan of theta. So we can say this our tangent of theta is greater than 1 upon mu cot of theta, and cot of theta we can write as 1 upon 10. Therefore we get that tangent square theta is greater than equal to 1 upon mu. And for our, therefore we can say that our this stick is not going to fall for this final condition. This is our, for the equilibrium. And now we come to our third question. The third question is somewhat similar, somewhat, not exactly, because here the other part is a massless. In the previous case both were having mass. So we are given a ladder of length L and mass m is hinged to the ground at its lower end. It makes an angle theta with the horizontal. A massless stick of length L is also hinged to the ground and it supports the ladder. The stick and the ladder are perpendicular to each other. Determine the force exerted by the stick on the ladder. So this is our basic question, and we can just draw the approximate figure. So we are having a ground, and here we are having a ladder, and this ladder is having a mass of m and its length is given as capital L. And somewhere in between it is connected to a stick which is making angle of 90 degree with it, and the stick is massless. This angle is given as theta and the length is of the stick is given as our L. So we can say this is our A, B, and let us call this as point C, and this is P. So BP is our stick and it is massless. And so let us, so other angle, this angle will be our pi by 2 minus theta, and let us say that our AP is equal to our S. So you can say that our AP is equal to S, and that we can write as our L cot of theta. That is quite easy. And now various forces we can define here, and first of all there will be normal at A. Let us call this as our NA, and there will be a force of friction, so let us call this our F, and there will be also a force that this stick is going to apply on the ladder, and its direction will be here, and let us call this our F. And also there will be mg in the downward direction. Other stick, that is our BP, is massless, so we are just going to ignore its mg, and its length will be our L by 2, and this will be coming as our L by 2 cos of theta. So in this case we are going to take the, you can say, calculate everything about point A, and if we are calculating about point A, obviously the normal NA, there will be no torque because of this, and also there will be no torque because of the friction. So we are going to consider two forces, mg as well as the force F. And this force F, sometimes we can also represent it as a normal because it is nothing but a contact force. So just we represent it as F because normal will be at many places. So let us consider that torque because of a ladder AC. You can say torque due to weight of ladder AC, and we can write this as a torque because of the ladder, so we can say G, and we have our its mg, and the lever arm is our L by 2 cos of theta. Okay, torque due to ladder AC about A, okay, about this point. And we can now come to our torque due to stick force, and the stick force we have to note it as F, and F is at a distance S, which we just calculated. Okay, so this is our distance S. Therefore we can say that our tau of F will be equal to our F multiplied by the lever arm, that is our S. S we already know, so this comes as F L cot of theta. And for equilibrium, you can say for equilibrium, torque because of the weight should be equal to torque because of the force F, and we simply substitute it. We get this our F L cot of theta is equal to mg by 2 and L cos of theta, and we are going to solve for our this F. Therefore we can say that our F is equal to, we get this our mgl upon twice small l, and cot is our cos upon sine, so cos cancels out, and we get this our sine of theta. So this is the value of the force that is the stick means our BP is applying to the ladder AC at point P, which was asked in the question. So this completes all the 3 questions. So in today's question, except the first part where we calculated by using the friction part, okay, and the next 2 questions was almost identical with each other, with the minor difference of our massless and mass. Okay. In the first case we calculated our friction, whereas in this case we calculated the normal force, or we can say simply the force. So this completes this all the 3 questions for today. Thank you.